Hello, my name is Dennis Hoppe. I'm Department Head for Service Management and Business Processes with the High Performance Computing Center Stuttgart in Germany. And today I would like to talk about the European project HiDALGO and how it addresses global challenges with HPC and big data technologies. And with me today is Derek Groen from the Brunel University in London, and he will then, in the second part of this talk, speak about pandemic research within HiDALGO itself. So, I mentioned global challenges. Basically, what are global challenges? So you see here a list of pictograms of global challenges that affect already or will have an effect on our society in future. So renewable energies and environmental health, for instance, which are both directly related to fight against the climate change and rising temperatures, or improve standards for education, or fight water scarcity. So these challenges are quite diverse but always affect our society. But it's just a selected group of global challenges that we are facing right now. And so the question that arises is if HPC can actually support decision making when it comes to global challenges. And yes, it can. So for instance, let's look at decision making, which is nowadays very crucial. When we look at the current pandemic, politicians need to make decisions like a soft or a hard lockdown, and they need to present to the citizens a concrete plan, how to circumvent the pandemic, and of course they need to defend the restrictions put onto the population. So overall, these decisions cannot any longer rely on gut feeling, and this is where HPC and AI come into play. So another challenge which is distinct to global challenges is that we need to bring various stakeholders having a completely different background and expertise together. So HPC experts with lacking knowledge about global challenges, global system experts often lacking knowledge about IT and HPC, and AI experts which are often not familiar with topics of GSC and HPC altogether. So, and in addition, global system challenges experts have completely different backgrounds as well. So it's very complicated to just bring all of these communities together. But this is exactly what HiDALGO aims to do. So HiDALGO is a European project. It was funded in 2018 and copes with these challenges. We have 13 European partners coming from 7 different countries. And the key objectives of HiDALGO are basically threefold. First, as I said, we need to improve the dialogue between these different stakeholders in order to, it should be fostered through user communities, for example, workshops and training activities. Secondly, we should use different infrastructures and the combination of them, like HPC, HPDA, and dedicated AI systems, just to implement these complex workflows imposed by the GC community. And finally, but not least, the project aims to advance integration of AI with simulations on HPC as well. So, and how does HiDALGO address these global challenges specifically? So global challenges address a novel way of complexity, which is based on various input parameters and thus produces vast amounts of data that need to be analyzed with both HPC and HPDA systems. Besides bringing communities together, as I mentioned, the overall architecture and platform of HiDALGO supports decision making by enabling highly accurate simulations, incorporating data analytics, AI, as well as data visualization into the workflow. Specifically, data visualization techniques are very important to approach stakeholders and explain decisions to a broader audience. So if you look further, HiDALGO also provides an easy-to-use solution in order to create these hybrid workflows, deploy these workflows on remote infrastructures such as HPC, HPDA. We are quite open which target infrastructures are supported. And the overall HiDALGO platform is also responsible for managing the data transfer coming from heterogeneous sources as well. For these features, we rely on well-established frameworks such as Cloudify, ecology, and CCAN for data transfer as well. So what is HiDALGO's ambition? I mentioned that already. So HiDALGO will basically be the single entry point in Europe for decision makers from the global system sciences, where we want just to have a platform where they can better connect with each other, and we also aim to train on these different communities as well, so that they can just make better decisions in future. Furthermore, HiDALGO takes existing methods such as agent-based modeling and simulations. So agent-based modeling and simulations, ABMS for short, as well as CFD simulations are combined in order to advance the state of the art with respect to these global challenges. A key paradigm that we rely on is the so-called coupling, so meaning coupled simulations. But what do we actually mean with coupled simulations? So you need to know, whereas previous global challenge applications solved quite simplified problems, HiDALGO aims to include as much data as possible coming from heterogeneous sources, as I said, to enrich existing models. Let's say we combine weather information with traffic data and additional real-time sensor information to improve forecasting of air quality in cities. And furthermore, simulations are coupled again with other simulations, with data analytics, with deep learning algorithms, or with visualization kernels to further improve their accuracy and decision-making capabilities overall. My colleague Derek can later on explain you, based on a real application, what coupling means in that context as well. So next I would like to introduce to you the pilots that HiDALGO is addressing during the project's runtime. And here you have very specific examples which global challenges are currently addressed by HiDALGO. So first we have the migrant simulation, which develops realistic models for simulating refugee streams. Second, there's a social network analysis, which is concerned with replicating the flow of messages through the social network in order to analyze the spread of fake news, for example, so the spread of messages in general. Third, we analyze urban air pollution through simulations. I gave already some example which data and simulations can be coupled in that context as well. And so originally HiDALGO planned to pursue these 3 pilots, but as a result of the COVID-19 outbreak this year, we decided to work in addition also on simulations to analyze and predict the COVID-19 spread based on the code that was developed in the migration pilot as well. So this is something that we address quite new, so we are quite adaptive and dynamic within the project as well to address these current and future global challenges as well. And overall, we have, of course, to comply with the GDPR rules. This is specifically true when we have to exchange so much data. For instance, the social network Twitter data, which then needs to be anonymized and then shared between partners as well. What is also in common throughout all pilots is basically that they rely on flagship HPC codes. In the case of FLE, the other way around. It's FLE in the case of migration pilot, IKIST in the case of social networks, and OpenFOAM in the case of urban air quality. And if you look at the COVID-19 simulation, it's FACS, which is also then executed on HPC systems as well. So as said, global challenges applications do not originally rely on coupled simulations as compared to the engineering area where it's quite common. So therefore the models are normally based on simplified problem statements, which are mostly based on probabilistic methods. So, and HiDALGO tries to improve that weakness by coupling mechanisms from different subdomains in order to increase the relevance and precision of these results. For this purpose, we differ between weak and strong coupling. Weak coupling would mean that we have some kind of sequential execution of applications. We share data via network files, database connectors, and so on, just to enrich simulations with more data as well. And strong coupling would be, for instance, that two simulation tools share the data via message pathing protocols or something similar. So on this slide, if we come back here, some coupling results are listed which are already realized. So for instance, the ECMWF, the European Center for Medium Range Weather Forecasts, provides HiDALGO pilots with weather and climate data through a new REST API. We support currently streaming data processing via Kafka. And as I said, the urban air pollution pilot couples basically agent-based modeling with common CFD simulations as well to improve the prediction of air quality in cities. So, and in addition to that, HiDALGO is also working on introducing AI into existing global system sciences workflows as well. But this is, again, a completely different topic, which we will not go into today. So, last but not least, for this introduction, I would like to conclude it with some benchmark results. Although I mentioned that all pilots exploit HPC flagship codes, this was not always the case when the project started in 2018. So basically, HiDALGO improved the scalability of all pilots and codes as the complexity of the solution also increased. So, and when I talk about complexity here, I mean to increase in resolution, number of aspects considered in the models, and coupling with other simulations as well. So for instance, with respect to the urban air pollution pilot, we have identified that ANSYS Fluent was not scalable as it was required by that pilot, and so we replaced it eventually with OpenFOAM and obtained quite some good results as well. So, and now I would like to hand over to Derek, who will give us some very interesting insights into how the spread of COVID-19 can be efficiently modeled using the HiDALGO platform.
So hello everyone, my name is Derek Groen, and I will discuss a little bit about a specific case study in HiDALGO, which is about modeling the spread of COVID-19 in local areas. This particular work is based on a publication that we published this summer in the Journal of Simulation, and you can find the reference at the bottom of this slide. So The central topic of this particular case study that we started working on in March in response to the pandemic in general, but also the lockdown and the epidemic in the UK, is a collaboration between the computer science department at Brunel University London and the HiDALGO consortium. And of course, it is in response to the COVID-19 outbreak which we are all pretty much aware of. The main idea of the project is we essentially were approached by an NHS, National Health Service organization in the UK, to develop a code that could model the spread of COVID-19 in a more local setting. So it's not a national code, but rather a code for a borough inside London, or it could be reapplied for a medium-sized city or a small region within a country. And the idea of the code is that it takes into account geographical properties and other local effects, and that it could be used by individual hospitals to modify their strategy in terms of service provisioning. So in that way, FACS aims to support the emergency response against the outbreak. And the idea is that with the code, you can rapidly test a range of public health interventions, but you can also provide reliable and reproducible forecasts in local regions. The main advantage really for modeling locally is that you can advise individual authorities and individual trusts or hospitals as to what to expect in terms of service load, but also what will happen when certain interventions are undertaken. Of course, a local model is also likely to be more accurate and precise than a global model, because in our case we are resolving local buildings and local establishments rather than using some synthetic graph that approximates this on a national level. For our simulation, we use an agent-based simulation development approach, which consists of 6 steps. First, we select a situation, which is essentially a region in a time period. Then we need a range of data sets that includes geospatial data, the connectivity between the places, epidemiological data and demographic data. The geospatial network is not so important at the moment, but the main thing we need is the boundaries of the region that we want to model. The epidemiology data is something that I will discuss in a moment, but essentially we use these 4 data sources to construct a model and make digital representations of these aspects. We then refine it, for example, enact measures or try out different scenarios. And then we use the FabSim3 toolkit and the FACS simulation code to run the simulation using supercomputers. And then after that, we validate it against what data is available when we provide forecasts in places where data is not available. FACS is stochastic and assumptions are very often uncertain, so we tend to run many instances of the code and then provide an ensemble forecast. The code itself is not parallelized yet at this stage because development only started in March this year, but we are planning to parallelize the code in the coming year so that we can model even larger regions. This is a short example of location graph that we load into FACS. You can see that there's a range of different locations like hospitals, houses, but also schools, parks, shopping locations and leisure locations, for instance, as well as offices. And we extract these locations directly from OpenStreetMap using their API and extraction scripts. Here on the slide you see an example of that for the borough of Brent within London, which consists of about 320,000 people. In terms of a simulation approach, there are 4 essential components or 5 essential components that constitute our approach. That includes, of course, the flu and coronavirus simulator, FACS, but also we have some principles that we derive in terms of input and output and algorithms from our flu migration code that we have been working on. As I mentioned, the agent-based principles are important, and then we also have the FabSim3 automation toolkit that we use, and of course the HPC infrastructure that make all these ensemble simulations possible. In terms of our disease assumptions, we store these in a YML file, which is human readable, and here on this slide you can see the current assumptions that we have. They are largely derived from existing literature and they're applied to individual agents. One notable assumption that we do not put into the model is the so-called R value, or the population-wide infection rate, because that is also an output parameter for the simulation. So instead of that, we have an infection rate parameter that indicates the probability that a susceptible person gets infected by an infectious person if they reside within 4 square meters for a 24-hour period. And this is based on a range of literature sources, for example, around cruise ships and prisons. And that's a more microscopic parameter that sort of has more inherent properties about the infectiousness of the disease. One aspect that we don't really take into account yet are weather and temperature related effects, and that's something that we would like to look into later. Here you can see the brief equation for our in-building disease model. This is essentially the equation that we use to resolve the disease within particular buildings. There are a lot of different terms that you can see explained on this slide, but I think the most important thing are the LSS and the LSI parameters. So essentially the LSS is the number of minutes that a given susceptible person stays in a location, and the LSI is the number of minutes that all infectious persons stay within that same space on the same day. On the left hand side you have the probability of infection. So what this equation explains is the probability that a susceptible person that visits this building is going to be infected. This equation is new. We basically developed it from scratch, and we actually also are still working on it to see if we can find a more elegant form of it. The facts code in a nutshell contains four different components. There's the main facts code that does all the simulation, but we also have a pre-processing module that is used to prepare the data files and the location graph, among others. The post-processing module that you can use for ensemble visualization, but also for validating it against data you may have acquired from municipalities or hospitals. And then there's the FAB COVID-19 plugin, which is very important because it enables us to run these large facts ensembles on supercomputers and other infrastructures. The main execution platforms for facts are local for testing, which you can do with a simple script. Of course, the computational capability is going to be limited, so you can't run very large ensembles. The runtime on a local machine is about 1 to 2 hours for most areas. And it's generally more favorable to run it on a remote resource, because then you can look at different scenarios and account for the stochasticity of the code. The main way that we do that is using the FabSim3 automation toolkit and a remote supercomputer, for instance, the Eagle supercomputer in Poznan. We also have approaches in the FabSim3 plugin to perform sensitivity analysis so that people can see which assumptions and parameters are particularly important in which phases of the epidemic. There's a third way of executing facts, which is using Cloudify and CCAN, which we don't demonstrate here, but essentially that's using sort of HiDALGO services, core services, and a more user-friendly way of running the code. The typical ensemble size tends to be the number of scenarios or interventions you want to look at times the number of locations you want to examine, and then times 25 to roughly account for the stochasticity of the code. In terms of supported location interventions, we have models for 8 different boroughs in London, as well as we are working on preliminary models for Madrid and Islamabad in Pakistan. And in terms of public health interventions, we support pretty much all public health interventions, but there are still some other features that are unrelated to that are under development. So we want to incorporate airflow dependent aspects in greater detail, and we also still want to add street level interactions. In terms of the model validation, we validated our forecasts against results in several boroughs, mainly Brent and Hillingdon. Here's a simple example of a validation test against Hillingdon, where the simulation ends up with slightly higher values than the validation data. This is very much an ongoing exercise, and we are basically validating on a periodic basis to see if we can get our models right. As for the simulation results, here's a simple example of what the outputs of the simulation can look like. So we plot the number of susceptible, exposed, and infectious populations over time. On the x-axis, you have the simulated time from the start of the simulation until the end, and on the y-axis, you have the number of agents in that particular state. And then, for instance, we would have different scenarios. So every row is the top row is susceptible, the middle is exposed, and the bottom is infectious. And in terms of columns, The first column is no lockdown measures. The second one is a lockdown then extended. The third one is a dynamic version of the lockdown. And the fourth one is a lockdown that is lifted and reenacted on a periodic basis. And the effects of the lockdown are most visible in the exposed populations, because those are the people that just have been infected with COVID-19. People are only infectious after approximately 3.5 days. So there's a bit more lag in that plot. In terms of our future plans, we very much want to apply the simulation to other countries and cities. So if you hear it and you hear this talk and you think, oh, I would like to reapply the simulation, please do contact us because we'd be very keen to help you out to repurpose the code. In our experience, it often takes a day or a few days to have a very first prototype of that. We want to parallelize the code. Initialization takes quite a bit of time. So we want to parallelize that first, and then after that probably would parallelize the mechanisms for visiting locations, as that is the most computational expensive component. We also aim to integrate our code with other simulators for hybrid modeling. We've already done a preliminary integration with the discrete event hospital model, but we also want to couple to other relevant models, for example, for modeling airflow in individual buildings. But in general, we want to work on improving the quality of the forecasting through sensitivity analysis, for instance, and also through extensive validation. So we also want to validate the code more widely. And with that, I basically covered everything. So thank you very much for listening. And if you have any questions, please don't hesitate to contact us.